Section 7.3, Simplifying Non-Perfect Squares. First, we have the product rule. And we can use this rule two ways. We can use it to multiply radicals. So if you are multiplying with the same index, you can multiply the numbers underneath. And these numbers need to be positive. This does not work if you have negatives under there. So if you have positive real numbers, multiply those underneath the radical. We can also use it, and we'll look at that in a few minutes, to break down a radical. So if we're here, we can use it to break down into separate radicals. Let's look at a few examples. First, we have square root of 6 times square root of 5. So by our rule, we can multiply them underneath the radical, 6 times 5, and get square root of 30. We can do the same with square root of 6 times square root of 6 and get square root of 36, which is a perfect square. It is just equal to 6. When we do a few of these, you will realize that when you get two copies of something, that is a square, and it will actually go out from under the radical. So anytime you have the square root of something times the square root of itself, it will just take the radical off. So it's a little shortcut you can use. Right? We can extend our rule to any index, and you will just keep the index. So cube root of 5 times cube root of 2 will give us cube root of 5 times 2 is 10. A couple more examples. This one we have square root of 8 times square root of 2. So we will multiply those underneath the radical. 8 times 2 will give us 16. 16 is a perfect square, so we go ahead and take that square root to give us 4. For next one is fourth roots. You can also use the rule for those. You will just need to keep the index, and they do have to be the same. So this will give us a fourth root of 2 times 8 is 16. And you might remember this is a perfect fourth power. 2 to the fourth is 16. So the fourth root of 16 is 2. Next we have the quotient rule, which says if you have a fraction under a radical, you can take that radical with the numerator and with the denominator. If we find later that we have common factors between the a and the b, we can also go backwards from this form to one radical to be able to simplify. So let's look at some problems. For our first one, square root of 5 over 36. We don't have anything in common there, so we'll go ahead and make two radicals out of it. So radical 5 over 36, and then we'll simplify if we can. There's nothing we can do with the square root of 5. It is a prime and it doesn't have anything to simplify. 36, though, is a perfect square. So we're going to keep this square root of 5 on the numerator, and we'll go ahead and take the square root of 36, which is 6. That is our simplified form of our answer. You can also use this rule for other roots. We will just need to keep the index with each one. So it's one fraction. We can split it and make separate radicals. So put the radical with the numerator and put the radical with the denominator. Cube root of 5, there's nothing you can do to simplify, so we'll just keep that piece. Cube root of 64. 64 is actually a perfect cube. If you remember when we made the chart, 4 times 4 times 4 gives us 64. So the cube root of 64 will give us 4. Here are a couple more problems. So we will also use the quotient rule. We will break this into two separate radicals. Keep the index, so fourth root of x cubed over fourth root of 16. For the numerator, there's nothing we can do there, so we'll keep that piece. And for the denominator, 16 is actually a perfect fourth power. 2 to the 4th is 16, so the 4th root of 16 is 2. And that one's simplified. We'll work the same way with the next one. This one is a square root. So we'll take a square root with the numerator and a square root with the denominator. We're going to be able to simplify on both of these. For the numerator, you can't do anything with the 13. But for the variable, the square root of x squared is going to be just x. So we're going to keep the square root of 13. But for square root of x squared, we can take the x outside the radical. You can put it there or you could put it in front of the radical. Either one is okay. Right. For our denominator, these are both actually perfect squares. The square root of 4 is 2, and the square root of y squared would be just a y. And that is simplified form. For our next couple of problems, we're going to use the rule backwards. So we are over here with separate radicals, and your clue to use this is because you have some common factors. 6 and 3 have common factors. If it was together without the radical, you could reduce. Same thing here. You see some common factors, x's and y's. So we're going to put it back together. 6 over 3. Simplify. 3 will go into 6 2 times. So we have square root of 2. And that is simplified form. We'll do the same with these variables. We'll put it back as one radical. And we can just work on the inside. Remember, when you have that fraction or quotient, the exponents subtract. So we'll put our radical. 5 minus 1 will give us 4. And 9 minus 1 will give us 8. Now, these are pretty high, so it might simplify more. What you can do is divide by the index. Remember, if you don't see an index, it is automatically a 2. So 2 will go into 4 2 times. So that will be x squared, and it will come out from under the radical. For the y, 2 will go into 8 4 times. Goes evenly, so it comes out from under the radical. So if we do this times itself, x squared y to the 4th times x squared y to the 4th, it would give us this x to the 4th y to the 8th. For our next example, we're also going to go backwards. We have separate radicals, but we can see some common factors in here. So if we put it back together, we'll be able to simplify some. So we'll make one radical. And we have 96 over 6, a to the 18th over a squared, b to the 4th over b to the 4th. So we'll just work on the inside. First, for our fraction, just reduce or divide. And 6 will go into 96 evenly, and it goes 16 times. For your variables, you're going to subtract the exponents. So 18 minus 2 is 16. And the b's are actually going to cancel because you're going to have something else there. You're not going to have to write anything for the b's. They're just going to wipe out. Right, now we'll work on this. 4th root of 16. 16 is a perfect 4th power. It is 2 to the 4th. So 4th root of 16 will be 2. And for our variable, we can just divide. 4 into 16 will go 4 times. So that one also goes evenly. And it comes out from under the radical. I want to give you some rules for simplifying radicals. So a radical in simplified form means first there are no perfect powers under the radical. So if it's a square root, you cannot have any perfect squares underneath. If it's a cube root, you cannot have any perfect cubes. Right. Second rule, no fractions can be left under the radical. Third rule, no radicals can be left in the denominator. And fourth rule, no common factors between the index and exponents under the radical. So we're just going to work on these a few at a time, and you may not see that last one for a little bit. There are two standard techniques for simplifying these radicals. One is to break to primes and see what factors are in there. And the second is to divide out any perfect squares. So you would have to know your list of perfect squares and see if any of those would divide into it. Both techniques are good. I'm going to go with the first one, breaking to primes. So we're going to use a factor tree, and we're going to break 96 down to see what it's made out of. So there's not anything easy for me with 96. It doesn't click, but I know there's a 2 in there because it ends in an even digit. So I'm going to break it down with 2 and just divide 2 into 96. It goes 48 times. And then keep breaking until you have all primes. So 2 is prime. 48, 6 times 8 clicks for me. Anything that works for you is fine. The 2 is prime. I'm just going to bring it down. 6 is 2 times 3. 8 is 2 times 4. And we have to break one more time for that last 2. I like to keep bringing these down so I don't lose a factor. That way everything on the bottom line will be all primes. Right. Once you have all primes, I'm going to put it back together under one radical. So I have 1, 2, 3, 4, 5 2's. And 1, 3. Every time I find a group of 2 copies of something, that is a perfect square. And one can go outside the radical for that square. So for my 2's, that's a group. That's a square. 2 times 2 is 4. Square root of 4 is 2. I can take 1, 2 outside for that. And the amount of copies in your group is determined by your index. So our index here is 2. So I look for groups of 2 factors. That makes a square. Right? I have another group of 2's here. That's 2 of them. So 1, 2 goes to the outside for that. It will multiply by anything out there. The other 2, I don't have any extra copies to go with them. I only have 1 copy of each. So they're just going to multiply back together underneath the radical. There is no longer any squares under there. Square root of 6 does not have any squares in it. So we'll just multiply 2 times 2 is 4. So 4 times the square root of 6 is simplified form. This is the type of answer that you need to give for these problems. They do not want you to punch it in your calculator and give a decimal estimate for that square root of 6. They want it in this form. Next, we'll look at square root of 80. 80 is pretty big, so it probably has something in there. We'll break it down. Anything that you can see that multiplies to give 80. So if it ends in 0, there's a 10 in there. That's a quick way to break things down. So I'm going to use 8 times 10. For 8, I can use 2 times 4. 10, I can use 2 times 5. And I have to break one more time for this 4. I'm going to bring the others down. I'm going to put it back under one radical. So 1, 2, 3, 4 2's. And 5. It is a square root, so I'm looking for groups of 2 factors to make a square. Here's a square. 1, 2 goes outside for that square. 1, 2 goes outside for this square. It will multiply with whatever else is out there. The 5 is left. It does not have anything to go with it to make a square. And just multiply the ones outside together. So it gives you 4 times the square root of 5. That is simplified form. We'll look at one more problem for this video. And so we have square root of 12x to the third y to the fifth. So we're going to break down. First for the 12, we will do 4 times 3. And you could do 6 times 2. It doesn't matter. Whatever clicks for you. 4 is 2 times 2. And 3 is already prime. For the variables on this particular one, I'm just going to write them out. So 2 times 2, I have a 3. X cubed means I have 3 x's. Y to the fifth means I have 5 y's. Now, it's a square root, so I'm looking for groups of 2 factors. Here is a group of 2. So 1, 2 goes to the outside for that group. That's a square. I can't do anything with the 3. It doesn't have a partner to make a square, so it's going to stay. For the x's, for 2 of them, I can take an x out. The other x will have to stay. For the y's, I can take a y for this group, and I can take a y for this group. There's still going to be 1 y left. All right, so we'll put what's under there left. We have a 3 left, we have 1 x left, and we have 1 y left. And multiply these that are outside. So I have 2x y squared times square root of 3xy. That is simplified form.